All right, now let's talk about how to work with significant figures. You've taken a measurement in the lab, and you've got the measurement, and you've got the significant figures. How do you figure out how many significant figures you have when you do mathematical operations? Well, there's two classes of mathematical operations. And the first are going to be multiplication and division. So for multiplication division problems, this is something times something else or a whole bunch of numbers multiplied together. The number of significant figures is set by the least significant number. So what you're going to do is look at each number that's being multiplied. So let's say you had 1.1 or 1.2 times 1.23 times 1.234. Our first number has two significant figures. Our second number has three significant figures. And our fourth number has four significant figures. So step one, count the sig figs of each and every number. Next step, go through and figure out who has the least number of significant figures. In this case, it's the 1.2. This is going to set the sig figs in our final answer. So no matter what we end up getting when we multiply this all together, our final answer can only have two significant figures in it. Same thing's going to be true of division. If you have 1.2 divided by 1.23 times 1.24, again, this is the number with the least number of significant figures. This is what sets the sig figs in your final answer. Addition and subtraction work differently. So let's say I had 1.2 plus 1.23 plus 1.234. Now for the multiplication division case, what we said is that it's set by the sig figs your sig figs are set by the least significant number. In the addition and subtraction case, you're set by the least precise decimal point. So in this case, we're precise to the tens, the hundreds, and the thousands. Now, like I said in a previous video, this can be 1.2, but it can go as low as 1.16, 1.15, and as high as 1.24. When we round, we're still going to get the exact same answer. We account for this when we look at the sig figs. We are set by the least precise decimal point. So this is precise to the tenths, which tells us that when we get done adding these together, we can be only accurate to the tenths. So even though the correct answer here is 3.664, we can only carry this decimal point, which will give us 3.7. Now, there are two other mathematical operations for which sig figs are not defined. These come into play when we start working with pH, much higher classes. If you're working with powers, meaning you raise something to a power like 2 to the third power or 2.97 to the second power, or you use a logarithm, so the natural log or the base 10 log, there are actually no rules for defining what those sig figs are. Typically, when you work with logs and natural logs, or you're working with powers, we just take 3 decimal points or 3 sig figs and that's it, regardless of the number of decimal points. Reason being, honestly, slides rules have 3 sig figs, so that's what we work with now, is we assume 3 sig figs if we know nothing else. Now, there is an exception to all of this, and the exception is if you're working with conversion factors. Now, the idea is that a conversion factor is known with infinite precision. Now, typically we don't work with infinite precision. Sometimes you'll see me work with atomic masses and I'll say 1.0 for hydrogen or 1.01 or 1.0073. Yes, that has a different number of significant figures. We always ignore significant figures though. We ignore significant figure contributions to a number when we're working with a conversion factor. So let's say we were converting, for the multiplication division case, 1.00 meters to millimeters. Well, we just multiply by 1,000, so this will give us 1,000. But the problem is that this has 1 sig fig and this has 3. Now, the conversion between millimeters and meters is that for every meter, there's 1,000 millimeters. And this looks like there's only 1 sig fig in this, one up here and one down here. Reality, it's infinite number of 0 meters is 1,000.0 infinite zeros millimeters. So again, we're going to assume that our conversion factors don't play a role. So when we report this number, we're actually going to put a bar over that 0 to signify that we have 3 sig figs here, and when we convert from meter to millimeters, we've still got 3 sig figs. If we have temperature, and we have 27 degrees, and we want to go to Kelvin, 27 degrees Kelvin, 273.15, our temperature in centigrade or in Kelvin looks like 300.15.
But we have to ignore these 2 decimal points because we're limited by the temperature in Celsius. Now let's say instead of giving you 27 degrees, I gave you 27.000 degrees centigrade. Now it looks like the conversion to Kelvin is what's limiting you. But again, this is a conversion factor. And so even though I really should stop here at the 0.15 because it's the least precise decimal point, conversion factors still don't matter. So even though this only goes to the 2nd decimal point because we've got 3 here, we need to carry 3 in the final answer. Again, this is conversion factor. For conversion factors, we ignore the rules. Now there is one other thing to note. When you convert your answer to the correct number of significant figures, so let's say you ended up with 27.0 plus 273.15, and your final answer was 300.15, and you want to get this back to 1 decimal point and you round. There's the engineering way of rounding, and then there's the scientific way of rounding. The engineering way of rounding is meant to basically cancel out error. So I think the rule is if it's an even number, you round down. If it's an odd number, you round up. We don't do that in chemistry. What we do in chemistry is, if you look at the decimal you're rounding, if it is greater than or equal to 5, you round up. If it is less than or equal to 5, or sorry, less than 5, you round down. So in this case, we'd have 300.2 degrees Kelvin. And that's your rules for working with Sig Figs.